remind you what we did last time. Last time we talked about, we started talking about velocity as the rate of change in position with respect to time. We talked about acceleration as the rate of change of velocity with respect to time. And we finished last time talking about rate of change of any function. So we talked about the following situation: f of x, any function. And we talked about such a function f of x2 minus f of x1, the change in values of the function f, divided by how much the argument of f changed, x2 minus x1. So how much the quantity f is changed, divided by how much its argument changed. And this was the rate of change of the function f from x1 to x2. And we said it was the average rate of change. So the average on this interval from x1 to x2, how fast the function was changing. And we have geometric description of what this average rate of change means on the graph of the function. And they always, for some reason, draw the same function. If we have x1 and x2 points on the x-axis, the values of x1 and f of x2 are values in the y-axis. The difference in values of f is this distance. Difference in values of x is this distance. The quotient is the slope of the secant line. So the slope of the secant line. So if x is a variable for time and f is the variable, the quantity which is a position, then this quotient will be the average rate of change of position, which we call the average velocity. If the function f is the velocity and x is the time, then this would be the average acceleration. But in general, we can talk about this quantity for any kind of function. It would be, I don't know, population on Earth, and x is time, then this would be the average rate of change of population of Earth with respect to time. It would be whatever. So for any function, we can form such a quotient, and we can assign this meaning to such a quotient. Also, we talked about instantaneous rate of change. How fast is the function changing at a particular moment of time? And we said that as we take the interval, the change in argument, as we make the argument change less and less, this average rate of change of function becomes closer and closer to instantaneous rate of change of this function. So as the x2 gets closer to x1, these motions that we remind a name, we call this quotient difference. F of x2 minus f of x1 divided by x2 minus x1 approaches the instantaneous rate of change of f at x1. And we also had geometric meaning for this notion of instantaneous change, instantaneous rate of change. If we have a function and we have a point x1 on the x-axis, well, the secant lines, as the point x2 gets closer and closer to point x1, they get closer and closer to the tangent line of this graph. So come closer to the slope of attention line. Slope attention x1, x1 at this point. So what we did was basically take our arguments about velocity, take our arguments about acceleration, and generalize them. Basically abstract them. Regardless of what the meaning of the function f is, we can still talk about the same quantities. Difference in f divided by difference in the argument would be the average rate of change of the function. If you make the argument change only a little bit, this average rate of change approaches instantaneous rate of change, how fast the function is growing at this point. So let's talk about some examples. Let's say my function is x squared plus x. And my question is, what is the average rate of change of f from, let's say, 3 to x. Let me start with from 3 to 4. So first question is, just from 3 to 4. Well, what does it mean? It means as x goes from 3 to 4, how much the function changes. We'll measure this quantity and then divide by the change in the argument, which is, well, the argument changed by just 1. So answer would be how much the function has changed as x went from 3 to 4 divided by how much x itself has changed, which is 4 minus 3. Function at the point 4 is 4 squared plus 4 20 minus f of 3, 3 squared plus 3, 12 divided by 4 minus 3, 1, which is 8. So very simple, how much the function changed divided by how much the argument changed. Any questions about this part? This is the simplest part and should be absolutely clear. Okay, great. So next, same but from 3 to x. So I want to understand, I don't tell you how much the argument changed, I just tell you that it changed from 3 to some unknown quantity x. What is the average rate of change of the function? Well, the answer is basically the same. Instead of 4, I'll just use not a number 4, but rather an unknown quantity x. So it will be f of x plus means the answer f of x minus f of 3 divided by x minus 3. And this works out to be x squared plus x minus f of 3 we computed plus 12 divided by x minus 3. So this expression can be used to find the average rate of change of the function from 3 to any number x. If you plug in x equal to 4, you'll get back this answer 8. If you plug x equal to 5, you'll find out what the rate of change was from 3 to 5. But in general, that's the expression for rate of change from 3 to x. Alright, so questions about this? now to the heart of the question. Now I want to know what is the instantaneous rate of change at the point 3. What is, well, the slope of the tangent line of this graph at the point 3. How fast the function is growing around the point 3. So, instantaneous rate of change at 3. Well, let's recall what do we mean by instantaneous rate of change. We said that if we want to measure how fast the function is growing at the point 3, I'll measure how fast it's growing, well, on average, from 3 to some point which is really, really close to 3. And then I'll make this interval from 3 to a point which is close to 3 shorter and shorter and shorter. So here I have one attempt from 3 to 4, the rate of change was 8. Now I'll measure the rate of change from 3 to the point x, which is really, really close to 3. One option would be, well, to take a calculator and compute what is the rate of change from 3 to 3.1, from 3 to 3.0001, and so on, and see whether we find a pattern. But now let's do it algebraically, without doing computations on the calculator. So what I'll do is like this. As x approaches 3, the average rate of change of f from 3 to x, namely this thing, x squared plus x minus 12 divided by x minus 3. So as I take my x closer and closer to the point 3, think about 3.1, 3.0001. What happens to this average rate of change, this expression? Well, yeah. Okay, so I'll do it in a second. Yes. So before this, I would try to argue, well, it will fail, but I will still try to argue in the simplest possible way. So, simplest kind of argument about such an expression would be, as x approaches 3, what happens to the numerator? Well, x squared approaches 9, x approaches 3, so x squared plus x approaches 12. Then this whole thing, the numerator approaches 12 minus 12, which is 0. Denominator, as x approaches 3, well, x minus 3 also approaches 0. So, unfortunately, the most naive argument of looking at the numerator and denominator and seeing what each one of those approaches doesn't quite work. The numerator approaches 0, denominator approaches 0, the quotient, well, it's just a quotient of two small numbers. Think about x being something close to 3, numerator will be a small number, something close to 0, not quite 0, close to 0. And denominator will be close to 0. So it wouldn't just work to plug in basically the point 0. They argue about what happens at the point 3. Well, but there is a reason why this numerator actually approaches 0 at the point 3. The reason is it can be factored out, and you can factor out simply x minus 3. That's what makes it approach 0 at the point 3. So let me try to factor out x minus 3. So, if I factor out x minus 3, what remains is, what is the other factor? X plus 4, yes. So I can see that it's x times x, x squared, minus 3x plus 4x plus 1x, minus 3 times 4 is minus 12. Once again, I already kind of knew one of the factors, x minus 3. I knew that this expression, when x is equal to 3, becomes 0. So it must be divisible by x minus 3. And the other one, I basically just guessed. I wanted, say, minus 12 to be minus 3 times the other number, so it must be plus 4. Okay. Next step, I'll cancel out stuff. So x minus 3 cancels x minus 3. And the result is x plus 4. I should be a little bit careful. This works every time when x is not equal to 3. There is exactly one point where this equality fails. It's wrong when x is equal to 3. Then this is 0, and you cannot cancel out 0 divided by 0. Never. But any other point, it works. Well, that's exactly what I need. I want the average rate of change from 3 to x when x is close to 3, but not quite 3. I'm not asking about the average rate of change from 3 to 3. That would be meaningless. But from 3 to a point which is close to 3, well, that's the answer. Turns out to be x plus 4. Now, as x approaches 3, I can argue what happens to this expression, x plus 4. It approaches a number. What number? So when x is close to 3, what can you say about x plus 4? It's close to 7. Yes, of course. So it turns out, well, this instantaneous rate of change could be computed without using the calculator, without arguments about what happens when x is 3.1, 3.001. Well, it could be made using the calculator. But here we have an even simpler way. If x is, say, 3.0001, I know what this average rate of change would be. Here's the formula. 3.0001 plus 4, 7.0001. If we want x even closer to 3, the answer would be even closer to 7. So the instantaneous rate of change is exactly 7. Alright, so questions about this? Alright, so let me turn up the level of abstraction one notch further. So next example would be like this. What is the slope of the tangent line to y equal to x squared at x comma x squared? So this question is geometrical. I give you a line, sorry, not a line, but rather a graph. Y equal to x squared is the graph of a function x squared. We've seen that it looks like this. On this graph, I choose the point x. Initially, the y coordinate is going to be x squared. So this is y and y is equal to x squared. And the question is, what is the slope of the tangent line? So for this question, I'll need, okay, first couple of remarks. The answer is going to depend on x. I chose x as an unknown quantity. Okay, so the answer is probably going to depend on x. If I measure the slope of line, tangent line at the point 0, well, the picture tells me it's going to be horizontal. If I measure it at the point 1, the picture tells me it's going to be, well, not horizontal, slope this way. I don't know what the slope is going to be, but it's definitely not 0. So the answer is going to depend on x. That's first observation. Second observation, well, why this question is about the stuff we are talking about. Well, slope of a tangent line is in fact the instantaneous rate of change of the function at the point, in this case, x. So, first remark. First step in our solution would be, let's choose the function f of x. F of x is going to be x squared. And we are looking for the slope of the tangent line to the graph of this function and the point x. We are looking for the slope tangent line to the graph f at point x. Alright, so let's go to here and see how can we find the slope of the tangent line. Well, we just argued that the slope of the tangent line, well, it's not really easy to find. It's what the slopes of the secant lines approach when the interval from x1 to x2 gets smaller and smaller. So first, we'll have to argue about the slope of the secant line. Alright, so slope of secant line through so one point would be x comma x squared, the point at which I'm interested to find the slope of the tangent. And the other one would be, well, some other point on the graph. Let's say x2 comma x2 squared. So on my graph, I choose 2 points. One is going to be x, the other one is going to be x2. And I'll measure, I'll compute what is the slope of secant line from x2 to x, from x to x2. Well, that's not hard. It's x2 squared minus x squared divided by x2 minus x1. So it's changing the y values, x2 squared minus x1 squared minus x squared divided by change in x values, x2 minus x. Alright, so that's about secant line. What about the tangent line? I should look at what happens to the slope as x2 becomes closer and closer to x. So next, as x2 approaches the point x, the slope x2 squared minus x squared divided by x2 minus x. Oh, does it approach anything? Once again, I'll start with the simplest possible argument. Maybe, well, we are lucky enough that just numerator approaches something non-zero, denominator approaches something non-zero, and then the quotient approaches the quotient of these numbers. So let's look. As x2 approaches x, x2 squared approaches x squared. And the difference is x squared minus x squared, so approaches 0. Denominator x2 minus x also approaches 0. So in the way this is written, it's not obvious what happens as x2 approaches x. It's just some small number close to 0 divided by small number close to 0. In fact, it was obvious from the picture that that's what would happen. Because you see, the difference in y values at this distance, difference in x values at this distance. As x2 is closer and closer to x, both quantities become really small. So each one of them is really small, but the quotient doesn't have to be small. In fact, algebra tells you what it is exactly. I can factor this thing out, just like I did in the previous example. So the reason x2 squared minus x squared becomes close to 0 as x2 approaches x is because it's divisible by x2 minus x. And the other factor is what's the other factor? I want to factor x2 squared minus x squared. The answer is x2 minus x times x2 plus x. Right. So I can use the formula a squared minus b squared is a minus b times a plus b. I will divide this by x2 minus x, like here. And then cancel stuff out. So the answer is x2 plus x. Once again, it works only for x2, which is not equal to x. So naturally, this expression, this quotient, is not quite defined when x2 is equal to x, because both distances will be 0. But for any other value of x2, that's the answer, x2 plus x. Now I can ask the question, when x2 approaches x, what happens to this expression? It approaches something. What is it? x2 is going to be close to x, so x2 plus x is going to be close to x plus x, which is 2x. And that's the answer. So as we expected, the answer is going to depend on x. Here it is, 2x. Let's see whether it makes any sense. So let's say answer slope is equal to x. Let's see whether it makes any sense. I know by just looking at this graph that at point 0, the slope should be 0. Does it work? No, 2 times 0 is 0. Another thing, looking at the graph, I see that as I go to the right, the slope becomes larger and larger. Is it the case here? Well, yes, as x becomes larger and larger, 2x also becomes larger and larger. Another thing, when x is to the left of 0, the slope is clearly negative. Is it the case here? Of course, when x is negative, 2x is also negative. All this doesn't say that we didn't make any mistake. Well, I hope we didn't, but we just checked that this answer makes some sense. So, what is the reason we had to deal with this somewhat abstract algebra? An unknown quantity x, another unknown quantity x2, which approaches the first unknown quantity x, then doing some calculations and so on and so on. What's the reason? Well, the reason is we got a very general answer. Not just the answer at one point, not just the slope at the point 1, 1, not just the point, the slope at 2, 4. We got the answer at any point x. If you want to know what is the slope at point 10, 100, the answer is 20. You don't have to repeat this thing over and over. Okay, so questions about this? Alright, so for a little while we'll stop discussing these things, instantaneous rates of change and slopes of tangent lines. We'll get back to this in about a week, but for now we'll start discussing just this kind of arguments. As this kind of arguments. As a variable approaches some number, what happens to some expression? And the concept behind this is the concept of a limit. So let's start looking about Alright, so limits is about what happens to some quantity maybe a quantity like this, as the variable approaches some number. So formally, the limit of the function of the expression f of x as x approaches some point a, so a being a number, so equal to L if as x gets closer and closer, if f of x gets arbitrarily close to L, as x gets closer and closer to A. And the notation is, in this case, you write limit of the function f of x as x approaches a is equal to L, or alternative way of writing it, f of x approaches L as x approaches a. So let me explain this concept a little bit more visually. So first of all, what did I write there? I'm saying that a function has a limit at some point, so when x approaches some number a, if it happens that the value of the function approaches some number L, then we say that the limit of this function at the point a is equal to L. What does it mean? Well, let's have a point a, let's have a number L on the y-axis. What I want is for my function to be really close to the point L when x is really close to point A. But not necessarily A itself. So maybe I should write here by node equal. So it gets close, but not quite A. So the picture would be like this. I want my function somehow to approach this point, in fact from both sides. What I don't insist on is that the function at the point A be equal to L. For now, that's not necessary. So at the point A, I don't care, but as x gets closer and closer to the point A, I want the function to get closer and closer to the value L. Well, the natural question is, why don't I just require my function at the point A to be equal to L and then be done with it? Well, the reason is, in many situations, like in this situation, the function is just naturally not defined somewhere. Say this function is not defined at the point 3. And there is nothing you can do about it. You cannot plug in x equal to 3 to this function because the answer is going to be 0 divided by 0, which is not defined. But nearby values, when x is close to 3, but not quite 3, well, give you some expression when x is close to 3, the function is close to 7. So let's if this is our first example. First example, limit as x approaches 3 of that very expression x squared plus x minus 12 divided by x minus 3. So this is the same as asking what happens to this thing as x gets closer and closer to 3. Well, the answer is exactly what we did before. We can't quite argue about the numerator and denominator separately because both approach 0. But once you factor something out, x minus 3 times x plus 4 divided by x minus 3. Now, because in limit computations I'm not talking about the value at point 3, only about values nearby, I'm allowed to cancel out this x minus 3. And now the answer is obvious. When x is close to 3, x plus 4 is close to 7. So this is basically the same example we had before. Just replaced new notation, new word, limit. But otherwise it's exactly the same. Let's have another example. The same limit, but now at x approaching 4. Same function, same expression, but the limit is going to be at the point 4. Well, there are two ways to approach this question. One would be to do exactly the same thing, but x minus 3 out, get this expression, get the answer, x plus 4, when x is close to 4 approaches 8. But there is a better way in this case. So if you look at this expression, you don't have to think about factoring anything out. If you just look at the numerator and denominator separately, they already contain the answer. When x is close to 4, the numerator is close to what? 4 squared plus 4 minus 12. So 16 plus 4 minus 12, 8. The numerator is close to 8. Denominator is close to 1 because it's close to 4 minus 3. So the portion is just close to 8 over 1, which is 8. So in this example, well, we didn't have any problem with the behavior of the function near the point 4, or for the record, not even at the point 4. So for this function, we didn't have to do any complicated algebra. By the way, what is the graph of this function? X squared plus x minus 12 over x minus 3. So what is the shape of this graph? It's not part of the limit computation. We already done with the limit computations. I just want to ask, well, theoretically, what did we do? So what is this function? How does it look like? Linear, yes. So we already simplified this function. For any value of x except for the value 3, this function is exactly the same as x plus 4. So the graph is just a line with y-intercept at 4 and slope 1. Well, not quite. It's not exactly this line. It is this line everywhere but at point x equal to 3. When x equal to 3, this function is not defined. You cannot plug x equal to 3. The domain of this function is all numbers except x equal to 3. The way we draw it on the graph is like this. We get to the point 3, and we put, well, we erase it and put a circle around it. Show that we explicitly prohibit x from being 3. So we explicitly delete this point. So what we did in the first computation, well, we argued that when x is close to 3, but not quite equal to 3, my function gets closer and closer to the value 7. In the second computation, we argued that when x is close to 4, my function is close to 8. In both cases, we did not argue anything about the actual value of the function at the point 3 or at the point 4. In the first case, we argued about the behavior of function as x goes closer and closer to 3. In the second case, what happened to the function as x is closer and closer to 4. So, as we approach this point. It just happened that the value of this function at the point 4 was exactly the same thing. Alright, so questions about this computation? Okay, so let's do one more example. Name it 2 to the power x minus 1 divided by x is equal to 0. So first of all, I'll try the same thing as I tried before. When x is close to 0, what can you say about 2 to the power x? What is 2 to the power which is really close to 0? Really small number. So first of all, what is 2 to the power 0? 1, yes. And when x is close to 0, 2 to the power of a small number is going to be close, well, to 1. So the difference is going to be close to 1 minus 1, which is 0. And then I divide it by a number which is itself close to 0. So a priori, I don't know what the quotient is. It's just a quotient of two small numbers. I don't know which one of them is the larger one. Are they equal to each other? Very small, another one just small. So I have no idea. Also, unfortunately, we are not advanced yet in the algebra for this question. So we wouldn't be able to just factor out something from the numerator, simplify it. Well, we'll get there eventually, but not yet. But even now we can compute this limit. We can argue what happens to this expression as x gets closer and closer to 0. Well, not quite algebraically, but we can do it using, well, experiment. So let's choose several values of x, which get closer and closer to 0. And let's compute what is 2 to x minus 1 divided by x. And let me pre-commit to choosing, say, 0.1, 0.01, 0.001. We don't have much time, so I'll stop with those three. That actually won't be enough. I want to argue what happens to this function as x gets closer and closer to 0, but not necessarily from one side. I can also approach 0 from the other side. So I'll also take minus 0.1, minus 0.01, and minus 0.001. For each one of these values, I'll compute the value of my function, 2 to the x minus 1 divided by x. So I'll just use a calculator. In a calculator, I can find what is 2 to the power x minus 1, then divide the answer by x. And here are the answers that I get. For 0.1, I get 0.71773. 0.01, 0.69555. Next one, 0.69338. For minus 0.1, 0.66967. Next one, 0.69075. Next one, 0.69290. So I chose to keep 5 digits. It was probably a little bit too much for this example. But let's see. What can I argue about this answer as x approaches 0? Just from these points. Well, I'll see that all of them are somewhere around 0.7. Somewhere. Is it 0.7 just because 0.7 is a simple number? Well, I would argue that no, it's not really 0.7. I see that this is more than 0.7. Next one is 0.69555. Next one is even smaller. So it looks like these values actually become smaller and smaller. As I jump over the point 0 to negative values, well, I'm still, so the values still get smaller and smaller. But they're somewhere around 6.9 something. So I would argue that this limit is 0.69. And just from this data, I wouldn't be able to tell what the third digit is. I would say it's somewhere between 2 and 3, might be 2, might be 3, I'm not quite sure. I see that these digits already stabilized, the third one didn't. So I would argue that this is 6.9, and the next digit is 2 or 3, but no more information. If you want to find out what this limit is even more precisely, well, choose even smaller values.